I'll post that link to Schoology, that video, just in case you couldn't see it out there, you guys. And for those people that missed it, please don't try it at home, just for legal reasons. Yeah, try it on your bike. Good idea. So these are notes. You do with them as you please. You do have the sample question there, and number 3 that we're going to do at the end. I'm going to do the theory right here. So consider a ball moving in a circular path as shown. Okay. So we got this green ball. It's going around in a circle here. What do you think the red and the blue arrows represent? Well, there's a red arrow there, Nate, you can see. The red arrow is pointed towards the center. It's a vector, and you'll notice that it changes. Like right now, it's kind of small, and then as it comes around again, the red arrow gets bigger. So what do you think that red arrow represents? It's kind of like the top. No. What does the red arrow represent? Centripetal force? Why do you say that, Josh? Just a guess? Is the value of the red arrow changing? Less at the top, greater at the bottom. Where do you think the centripetal force is less? At the top, right? Think about, do I have it here still? Or did I take it back with me? Oh, I took it back, I think. Think about the rubber stopper on a string, right? Where does it get weak? Where does it get slack? At the top, right? Where there's very little centripetal force. And as it comes around to the bottom, it gets bigger. So yes, the red arrow is, I should do it in red maybe. The red arrow is the centripetal force. What do you think the blue one down here represents? You may not even be able to see it. It's right down here. What happens to it? It's always pointing which way? It's always pointing down. So what is the blue arrow? Gravity. You know what I say about gravity, right, Nate? Don't let it get you down. What happens to the speed of the ball? You may not have noticed. Look again. Does it change? Where is it going slower? Yeah, it's going to slow down on the way up as it's fighting gravity. And then on the way down, it's going to speed up. Right? And it's going to sort of, not stop, but when is it at its slowest? Right there. It's at its slowest at the top, which tells you that it's likely at the bottom traveling its fastest. Now, is this uniform circular motion? No, because uniform means constant speed, right? Now, you may see questions where it talks about vertical motion or vertical UCM. It's not uniform in that sense, but it still follows some of those general rules. What happens to the tension in the string? Well, I think you know that it's less at the top and more at the bottom, right? I think everyone can sort of agree on that, just sort of gut instinct kind of thing. Okay, so here's sort of one very similar, a bit more detailed with the math kind of thing. You'll notice that the speed, let's just watch the speed here. At the bottom, the speed is up over 25, and at the top, it's down to about 16. You'll notice that the tension at the top is all the way down to less than 2, and at the bottom, it's more than 7. What's up? Exactly. If we speed it up, what happens to the tension? It gets greater, right? And you can see this value of T here, right? As it gets to the bottom there, it's much higher. As it gets to the top, it's much less. So I've just sort of confirmed it in this little app kind of thing. Okay, so let's do the math now. Do you want to draw this picture? Okay. You might. Go ahead and draw. I'll do attendance. Okay, you're likely wondering what these different things represent. So at the top here, we've got V for velocity. We're going to assume this object is moving counterclockwise. Cole, did you really start a game? Like, seriously? No? That's one word. Okay, going counterclockwise. So V is the velocity here at the top. V is the velocity here at the bottom. Is the velocity the same? No. So in fact, we should maybe label this V max. It's a maximum velocity there at the bottom. And then this would be V min, minimum velocity, right? The FW, you know, already stands for weight force. So it's the force of gravity. It's acting downward, downward. I'm going to call this FS1 and FS2, string force, okay, tension. So the tension at the top is towards the bottom, and the tension at the bottom is towards the top. So where is it fastest? At the bottom. Where is it slowest? At the top. That's a key thing to keep in mind. If the math sort of doesn't work out, look at your positives, your negatives. Try to make that always happen so that it's fastest at the bottom, slowest at the top. And where is the tension the greatest? At the bottom. And it's less at the top. Okay, makes sense from a sort of a theoretical sort of standpoint? Okay, so now here's where it gets a little weird. Don't write, just watch for a second. So at the top, FCT, total centripetal force. Let me just make it a smidge bigger because it's kind of small. The total centripetal force is the string force, the string tension, plus the weight force, right? And the string tension is provided by the centripetal, I was going to screw this up. The total centripetal force is mv squared over r, but because the v is at the top, it's a minimum. So the total centripetal force is mv squared over r, where v is at a minimum, and that's equal to the string tension plus the weight force. And the centripetal force, the string tension, and the weight force are all down or negative. Okay, now you can write it. Okay, so now we're going to do the same thing at the bottom. Okay. So centripetal, I guess this FCT stood for top, centripetal force at the top. Centripetal force at the bottom, again, is made up of the string force at the bottom, plus the weight force. Again, the total centripetal force is made up of mv squared over r, and that's equal to the string force at the bottom plus the weight force. But you'll notice that the centripetal force is up, the tension is up, but the weight force is down. Okay, so this is kind of the same idea when we did in grade 11. You got weight force here, you got normal force, and if you're lifting, if you're pulling up, you're reducing the normal force, right? Same idea here. We're reducing the tension at the top by allowing the weight force to sort of assist with the centripetal force, and at the bottom, we're increasing the string force because it has to counteract the force of gravity. Since Vmax is greater than Vmin, then the string force at the bottom is greater than the string force at the top, and it would appear that I've changed my description here. So Fs bottom is greater than Fs top string force. In other words, the string tension is greater at the bottom. And we know that sort of intuitively. This is sort of a mathematical proof, I guess you could say, of that. Okay? Where we're headed here is we're going to come up with a formula that will help us find out the string tension, and we're also going to come up with one that tells us what's the critical velocity, how fast do you have to be going around in a circle to maintain that circular motion, which is exactly what that professor did for the stuntman. Okay, so this implies that there is some velocity below which the ball will not move in a circular path, and the string will slacken at the ball's highest point. Okay? Or it would be the same as if the car did not have enough speed to make the loop-de-loop. There is some value, some minimum speed that we have to go at, right? If we don't go fast enough, then there's not enough centripetal force to maintain motion. Yeah. You don't want that to happen. Not if you're the driver. Okay. So the minimum value is when the string force is equal to 0. Let me just do some cover up here. Where is it? How come I always lose it? I had it before. Oh, well, whatever. The minimum value is when the string tension is 0. As think about the rubber stopper, I usually have it with me at this point. As it goes around, right, that string tension decreases. When the string tension is 0, then there's just enough speed for it to maintain. If it's less than 0, then it collapses and there's not enough centripetal force. So when the string tension is 0, At this time, the ball just makes it around the circle. So FC1 at the top, FCT, T. If the string tension is 0, then the centripetal force, mv squared over r, is equal to gravity. You'll notice that what happens to the m's, Nate? They disappeared. So did the mass of the guy in the car matter? No. Okay. You'll notice that they did use a really small car, probably for other reasons. Maybe safety, maybe it was easier to get up to speed, cheaper, who knows, right? But the m's disappear, and you end up with v squared min over r is equal to g. And if you solve that for r, you get v equals square root rg. And if you had good eyesight, you would notice that that formula was on the board there in the video. I think it was a capital R. This is known as the critical velocity. The critical velocity. Because it's critical that you, FST, top. Okay? The critical velocity is the speed that you have to maintain to keep going in that circular path. V equals square root RG. G stands for 9.8. R is radius. That's the only thing that matters. The mass doesn't matter. Now, as you'll see in the next day or so, this is applicable to engineers building roads as well, which we'll get to eventually. Not that they're going to build roads that go up in a vertical circle, but similar idea here with this critical velocity. Good? Good to go? Okay. This value of v min is called the critical velocity, as I pointed out. It depends only on the radius of the circle and the acceleration due to gravity. It does not depend upon the mass of the object in motion. A satellite in orbit around a planet moves with the critical velocity for its radius of orbit. So when we put satellites up there that orbit the Earth, we have to put them at exactly the right speed, that critical velocity, so that it maintains circular orbit. If we have it at a greater velocity, what's going to happen? Orbit's just going to get bigger and bigger and bigger, and eventually it's going to like leave our gravitational field. It's going to leave the solar system. If it's too small of a speed, come back to Earth. That's never happened, but there have been satellites that have crashed Earth. Skylab was one of the first major satellites, like a space station. It crashed in Australia. I think it was the late 80s that they actually had to do fairly complex calculations to figure out. They saw the orbit decreasing, and they had to figure, okay, where's this thing going to land? They were worried that it was going to land on land. It did, but it was in a remote part of Australia, so it blew up. I think so. Anyways, I'll have to, that's a good question. I'll have to look that up, but I think that's what happened. It's been a long time. I think it killed a few dingoes. Yeah. You should have this one in that little package of sample questions from yesterday. If you don't have it, you can write it down. I'll give you a second here. So you will have to solve problems with that square root RG thing. They're pretty straightforward. I don't think I need to do a sample question there. It's just square root RG. Pretty easy. But this time here, we've got a 0.5 kilogram body. It's moving in UCM. That UCM is sort of in air quotes there because we know it's not uniform. In a vertical circle, so make sure you check here to see what kind of circle it is. The radius is 1.5 meters. The period is 0.5 seconds. We're going to find the speed of the body in orbit. It's actually the v bar, the average speed, right? No. Yeah, I'm not pointing at the kg. I'm pointing at where it says speed of the body, v bar. No. I'm just putting a little line, a little arrow. Speed of the body in orbit, average centripetal force needed to maintain this motion, the string tension on the mass at the bottom, and the string tension when the mass is at the top. Okay, so let's begin with when you're in a circle, right? The distance traveled is circumference, so that's going to be 2 pi r divided by the time, which is the period, which was given. It's not always going to be given to you. So we've got so this is the average speed of 18.8 meters per second. 18.8 meters per second. Again, that's the average speed. It's going to be greater at the bottom, less at the top. To find out the average centripetal force needed to maintain the motion, we're going to go with centripetal force is mv squared over r. We're going to use average speed. The mass is 0.5. The velocity is this number here, 18.8. So we get an average centripetal force of 118 newtons. 11. Speak a little louder for the microphone so we can send it to. What's her name? Nothing. Yeah. Okay. String tension when the mass is at the bottom. Is the string tension going to be more than 118? No? We've got 118 is the average centripetal force. So actually that's at the side. So at the bottom here it's going to be more, right? It's going to be more. I'm debating here how I want to do this, right? So the net force is that 118. That net force is made up of... No, I'm just going to call it the string force, Fs, plus the weight force is going to be that 118. Now you have to think about what direction is the centripetal force at the bottom. It's up, right? So that's going. That 118 is going to be positive. Maybe we should just put a positive there to sort of the net. Well, because it's all equal to each other. Plus 118. Okay, so we're solving for the string force. The weight force is going to be mass times gravity. Yeah. Not sure I understand. Yeah. Well, the question asked for the string tension when the mass is at the bottom. So this centripetal force is really just the average, right? And the average is going to occur. What I was saying here was the average occurs at the sides, right? Yeah. Okay. Good question. That's okay. Good question. So string force plus mass times gravity is plus 118. String force plus the mass was 0.5 times minus 9.8 equals 118. And now when I take that negative value, I'm going to have, and I'm writing it out way more than I need to. This is going to be minus 4.9. Oh, thanks, Nate. It is helpful when people show their work, isn't it? remember who your grad MC is.
Are you? Your MC? You better mention me at least once.
I'll probably have to tell you to be quiet, so yeah, there's a good chance I'll mention you.
Okay. How are you tell me to be quiet? So many other people.
Nate, you're ready to be quiet. I'm talking up here. I've got a microphone.
Wait. Are you telling me that?
No. The frown of disapproval. No, I'm not doing that.
Oh.
122.9. Oh, now, have I been on pause the whole time there? Hopefully not. Okay, so what's going to happen, part D, I've got to get done here so you guys get time to work. What happens at the top? Exactly the same thing, exactly the same logic. The only difference is at the, just give me 2 more minutes. At the top, that net force is down. So you're going to have the string force plus mass times gravity is equal to minus 118. Nate, 2 minutes. Right? At the top, in blue here, the centripetal force, the overall net force is minus 118. And so when you go Fs, you get that 0.5 times 9.8 is minus 118. You're going to have minus 118 plus that 4.9. I'm doing, Oh, maybe. I'm almost done. I'll see if I can get it through with it. It's not too bad. I just have to be careful when I, That's a plus. You get amused by small things, Nate. Okay, so string force at the bottom is more, plus 122. String force at the bottom is actually down, negative 113 less. Not particularly challenging. And I think the square root RG questions are pretty straightforward as well. The questions are kind of weird. They talk about satellites and stuff like that, but the solutions are there. I'll help you with them if you need. So I will stop talking and give you some time to work. Based on what I'm hearing, I'm going to keep going this week. We'll try to get through as much UCM as we can, and when we're ready for the test, then we'll write it.